Okay, so we would like to compute a vector line integral. And actually, it might be a good idea to introduce vector line integrals and explain how they work. So uh, let's talk first of all about two-dimensional vector line integral. So in two dimensions, um, or rather in two dimensions, not two-dimensional. So imagine that we have an oriented path. So it's important to um, make sure that we have this distinction from a scalar line integral. So we need our path to be oriented. And we have a vector field defined around that path. It's more important actually that it's defined on the path. Then we would like to explain the meaning of this integral. It can be written either as f dot dr along C or pdx plus qdy along C. And here I should note that when the path is closed, we actually use this little circle on the integral to denote that. In our case, the path is not closed, so we're not going to use this. And actually, there is more notation than one could find. So you can also find this as f dot t ds. So there are three different pieces of notation that you will have here. So the bottom line is that the computation of such an integral is done by means of a parameterization from an interval AB. This parameterization has to be compatible with the orientation. Remember that the parameterization is really a function that tells us how to traverse a given path. So it has to be traversed in the given orientation. And if all that is true, then the integral of FDR along C is going to be the integral from A to B of f of r of t dot the velocity r prime of t dt. Okay, so this is what it's going to be. And it also has a nice physical interpretation. If f is a force field and r is a path, this integral gives us the work of moving an object along that path. So let us also note that if we change the orientation, then the integral is multiplied by -1. So if you are in a situation where you know a nice parameterization that, however, gives you the opposite orientation, there's no need to worry about it. Just do the computation and then multiply the result by -1. In any case, let's see how we compute this particular integral. So the idea here is that we have to put together this integral right here, which means, if you think about it, that we need to find the parameterization. We need to identify the vector field and take their composite. We need to take the velocity, then take their dot product, and finally integrate it. So let's do all these things. So first of all, let's draw the path. Let's try to understand what we have in our hands here. So we have a part of a parabola. So that is going to be y is equal to x squared. And it's from 0, 0 to 1, 1. So it's implied that it's traversed this way. And the parameterization here is what we usually refer to as graph parameterization. So this is going to be t comma t squared for t between 0 and 1. Okay, and the velocity here is obviously 1 comma to t. Please note that the domain of the parameterization is a very important component of these considerations, and it has to be given. How about the underlying vector field? What is the underlying vector field? Again, let's go back to our integral. So whatever sits in front of dx will be the first component. Whatever sits in front of dy will be the second component. And please understand that these integrals with this notation allow us the freedom of putting dy first and then dx. So you have to be careful what you take first and what you take second. So here in our case, it's x comma xy squared. Okay, so that's the underlying vector field. And if we compose this with r of t, then we get f of t comma t squared, which means wherever you see an x, replace it by t. Whenever you see a t squared, replace it by, I'm sorry, y, replace it by t squared. So this is going to give us t. T times t squared squared. And this is going to be t comma t to the fifth. Okay, so now we can take together the dot product. Which is going to be t comma t to the fifth dot 1 comma 2t. And this is going to give us t comma, oops, it's a dot product, sorry about this. So what we get is obviously a scalar function. So this is going to be t plus 2t to the sixth. So this is what we need to integrate on the interval of the parameterization. So from 0 to 1, t plus 2t to the sixth dt. This is going to give us t squared over 2 plus 2 times t to the seventh over 7. Going from 0 to 1, this will be 1/2 plus 2 to the 2 over 7. We can clear denominators here, so we get 7 plus 4 divided by 14, also known as 11 divided by 14. And that's it. Thanks for watching.